Hi everyone and welcome to this lecture. In the past lecture we saw how we can deal with a repeated eigenvalue when it comes to solving system of differential equations, and today we are going to see the same thing, but today's case will be a bit different because as you can see I have already written it down. I'm calling it the deficient eigenvalue case, and we will try to see what does this deficiency mean and how we can bypass it. So again, the best way to do it is to see an example, and obviously this is not the most general kind of example, so please keep in mind that this is not the most general kind of example and this will only work for a 2 by 2 system. So let me write that down. So only 2 by 2 system, that means you have two variables x1 and x2, things like that. So let me first write down the system that I'm considering today. So this will be x1 prime equals to minus 1/2 of x1 minus 1/2 of x2, and x2 prime is just 1/2 of x1 minus 3 by 2 of x2. And again you can easily see that the coefficient matrix is just minus 1/2 minus 1/2 1/2 minus 3 by 2. And since this equation is in a format of capital X, which is a column vector, and if you denote it with the prime, that means the column vector is consisting x1 prime and x2 prime of ax times x. If you recall that this x was just this thing, x1 and x2, and x prime was just x1 prime and x2 prime. So again we try to proceed as before, and we want to set the determinant of A minus R I, where I is a 2 cross 2 matrix, to be 0. And if you do that and carry out the calculation, you will see that this will yield R square plus 2R plus 1 equals to 0. That means R plus 1 whole square equals to 0. That means R equals to minus 1, where this minus 1 has an algebraic multiplicity of 2. And we discussed what is algebraic and geometric multiplicity in the previous lecture. We also saw how this comes to be, and since there is only one eigenvalue and it's repeated 2 times and this is a 2 cross 2 matrix, so we expect to have 2 linearly independent eigenvectors. But can we actually achieve that? In the previous lecture we saw that there were one distinct eigenvalue and there was this eigenvalue r equals to 2 that got repeated 2 times, and fortunately we were able to find out 2 eigenvectors in terms of some free variables. But let's see today if we can do that. So let me just try to proceed, and if you proceed, what you will see is that it will have 1 minus 1/2 minus 1 minus 1/2, then there is a plus 1/2, and there is a minus 3 by 2 minus 1. There is this x1 x2, and they will yield to 0. That's how we find our eigenvectors. So let's try to proceed with this thing. So if you simplify this thing, this will be minus 3 by 2 1/2 minus 1/2, and finally you will have a minus 5 by 2 over here. Yes, minus 3 minus 2, so that's minus 5 by 2. x1 and x2, this becomes 0 0, right? Okay, now do these things. Oh yes, I made a mistake, I'm sorry about that. Instead of minus 1 there should be a plus 1. I'm really sorry about that, because this eigenvalue itself is minus 1, so this should be plus 1. Sorry, I need to get rid of this section over here. So again, minus 1/2 plus 1 is just 1/2. This will be 1/2, this will be minus 1/2, and this will be minus 1/2. And there is this x1 x2 equals to 0 0, and you can see that both of these rows is giving me the same piece of information. So I'll have 1/2 of x1 minus 1/2 of x2 equals to 0. So that means x1 equals to x2. And let's call this eigenvector as v1 or just v. And x1 is equals to x2. So instead of x1, I can directly write x2. And x2 is arbitrarily determined. So this is arbitrary. And you will have this x2. And obviously you can choose any values of x2 you want. So let's just go with x2 equals to 1. And this will yield 1, 1. And you can see that there is no way I can get another eigenvector from this. So this phenomena is known as deficiency. So what does this deficiency actually means? Because in the past example, that is on the previous lecture, we were fortunate enough to find out 2 eigenvectors from the repeated root. But here we see this repeated root, but we get only 1 eigenvector. So that's why we are calling this phenomena as deficiency, because we have no clue what the other eigenvector is, right? So this is where, when the eigenvalues are deficient, in this kind of case, these eigenvalues are called deficient eigenvalues. In this case, we have to introduce the notion of generalized eigenvalue, and this will help us to find the other eigenvector. And let me show you how this procedure works. So what we do right now is that instead of seeking a solution, to the system of DE as x bar, this bar means a vector that was written as v e to the power rt, we seek a solution. So let me write it in a different color so that you can understand that this is a different case. So we now seek a solution in the form x bar, that means the vector, it's a column vector, u bar plus v bar t e to the power rt, where r is the repeated eigenvalue, u bar is a constant column vector, and v bar is the solution that we already found. So this is our v bar. And let's try to see if this kind of solution will work. So the first thing we'll do is that we're going to differentiate this expression. So let's call this expression as 1. So we differentiate 1. And if you do that, this will turn out to be b plus, that means v bar, sorry, r0 u plus v t vt. Obviously there will be bar over this just to denote that this is a column vector, e to the power rt, where r is the repeated eigenvalue. Okay, now we are going to use this result in our differential equation. That our differential equation was in the column vector notation, something like this, right? That's what we're going to use. So if you do that, the left hand side will be v bar plus r0 u bar plus v bar t e to the power rt equals to a, and x bar will be just u bar v bar t e to the power rt, right? And this e to the power rt is never 0, so we can cancel that out. Okay, and finally what we will be left with is that so finally what will be left with is something like v bar plus r0 u bar plus v bar t sorry, it's not r0, sorry, it's a mistake, I'm sorry for that. It should be r, I wrote r0 for some weird reason. So yeah, this is just r, not r0, because if you differentiate it, this r will just come downstairs. So yeah, and this will be just a u bar plus v bar t, put a bracket over here. And obviously we also remember that since this v bar came from the equation a v bar equals to r v bar, this is the thing that we're going to use into our advantage, because if you take this, then our third line over here will be something like v bar plus r u bar plus r v bar t is equals to a u bar plus a v bar t. And now we are going to use this to our advantage. Instead of av, we are going to write this as r v bar. So again we have v bar r u bar r v bar t, and you have a u bar, and instead of a v bar, now we are going to write r v bar from here, and these two terms cancel each other out. And finally what we can see is that we have a u bar minus r u bar is equals to v bar. And finally, if you take u bar as a factor on the right side, because this is the column vector, you can write it as a minus r. Obviously there is an identity matrix over here, u bar equals to v bar. So finally we can see that yes, it's possible to find a u. So we write it's possible to find this u bar. Okay, and this u bar is known as the general eigenvector. Obviously the theory for this general eigenvector thing is pretty deep, and we're not going to touch anything of that. We are just trying to solve some differential equation. And now to complete the solution, we just need to find this u bar, right? So how can we do that? Since we already have our v, that is this v bar thing, we can obviously construct this u bar. So again, let me just remind you what v bar was. So v bar was this one thing over here. Our eigenvalue, that is r, was -1, and this was our coefficient matrix, right? So let's try to solve them. So let me denote, let me switch to another color. So now we want to solve for u. Solve for u bar, and obviously we remind ourselves that r was equals to -1, v bar was equals to 1 1. Let me denote the entries of u as u1 u2, and our coefficient matrix a was simply -1/2, -1/2, 1/2, and -3/2. And now we are going to use this equation over here. Okay, so this will be the equation to use. And if you do that, that means a minus u, sorry, not u, a minus r. Identity is just the 2 cross 2 1 because this A is a 2 cross 2 matrix. U bar is equals to v bar, and this is just minus 1/2, then 1/2 minus 3 by 2 minus, since r itself was minus 1, so write -1 -1 0 0, this whole thing. And u bar is the thing we want to solve for, so write it as u1 and u2, and v was just 1 1, right? And if you do that, this is just simple matrix algebra. So there is a minus over here and another minus over here, so this will be a plus, so minus 1/2 plus 1, right? And this is just 1/2 minus 1/2, this is just 1/2, and this is also minus 3 by 2 plus 1, and u1 u2, and this is equals to 1 1. Now you just need to solve for u1 and u2. So you can see that this is 1/2 1/2 minus 1/2 minus 1/2, u1 and u2 equals to 1 1. Again, same thing as before. So you will have u1 by 2 minus u2 by 2 equals to 1, right? And in the bottom below, they will yield the same thing, if I'm not mistaken. Yeah. So what we can do is that u1 minus u2, we can take it to be 2, and we can write u1 is equals to 2 plus u2. Now obviously you can take any of this thing, that is u1 or u2, to be a free variable, because there are two variable and one equation, one effective equation. So for simplicity, since we only want one of the u vector, because for many choice of u2 there can be many u1 and there can be in total many u vectors, right? Because if you write the u bar, this will just be 2 plus u2 and u2, like this. And for different choice of u2, you are getting different u bar, but we only need one u bar. And the most simple choice is just taking u2 equals to 0. It's an arbitrary choice, it's a free variable, so it's an arbitrary choice. And if you do that, this will be just 2 0. Obviously you can take u2 equals to 1, u2 equals to 2, whatever the heck you want. So we are done with finding this u bar, and finally we can write our solution, that is x bar, that is a column vector. That's why I'm using the bar, so that you guys don't get confused. This is the kind of solution we tried, right? And finally we're going to write that. Sorry, not this one. Yeah, this is the one. This is the kind of solution that we tried, and finally we're going to write that. So our x bar was just u bar plus v bar t e to the power rt. Now I'm just going to write u as 2 0, that is u bar, and v as 1 1, t, this whole thing multiplied with the e to the power minus t, because r was equals to minus 1, and this will be x1 and x2. And now you can just do the matrix algebra and find the solutions for x1 and x2 individually. So this will be just 2 e to the power minus t plus t e to the power minus t, and here it will be 0 plus t e to the power minus t. So you can finally write x1 as 2 e to the power minus t plus t e to the power minus t, and x2 as t e to the power minus t. So this is how we can deal with the deficient eigenvalue cases. All you need to do is that you need to assume a solution like this. And this is only valid. So let me just remind you the important fact that the discussion we had today is only valid for a 2x2 system. When you go to 3x3 system, you need to modify this idea a bit more, and obviously there is a most general rule, but that is out of our context for this course. And yeah, this will be it for today, and I'll see you guys in the next lecture. Thank you.